Below, this is the teaching presentation for my assigned practice problem. Here's the problem. So for the first part, part A, it asks if the speed of the object increases, decreases, or stays the same. Well, if we look at the graph, we can see that as you move from left to right on the x-axis, the y values increase, and since the y values represent velocity, we can say that velocity increases. The next part asks us to give a statement on the magnitude and direction of the acceleration. From the following picture, we can see that when the object is let go, it will go down because of gravity. Additionally, we know that from the first part that the object is speeding up as it is moving down. Given these two details, we can conclude that the object's acceleration is downwards. In order to know how the magnitude of the acceleration changed as the object fell, we can visualize the tangent line of the graph as time increases. Whatever changes happen to the tangent line will reflect changes to the magnitude of the acceleration. As you can see from those tangent lines, they get less steeper and steeper as the object falls, meaning that the magnitude of the acceleration gets less and less as well. Now that we've observed what happens to the magnitude and direction of the acceleration, our final answer will say the following. The acceleration of the object is downward because the object is moving down and is speeding up while moving down. The magnitude of acceleration is decreasing because the slope of the velocity versus time graph is decreasing as the object falls. The last part of part A asks to find an approximate value for the magnitude of acceleration as t equals 0.20 seconds. In order to answer this question, we need to draw a tangent line at where t equals 0.20 seconds. Now we need to select 2 points from the tangent line. So our points will be 0.25 and 0.85, and 0.16 and 0.65. Now that we have our points, we can now calculate our slope with them. So we plug our values in, and we get 2.22 meters per second squared. Now for part B, the first part asks us to derive an expression for displacement of the falling object as a function of time. Since we are given the equation for the falling object's velocity as a function of time, all we have to do is integrate that equation to get our answer. So here's our velocity function. We can rewrite v as dy over dt since velocity is the change in y over the change in time. Next, we multiply both sides by dt. Then we integrate both sides. On the left-hand side, we technically have the integral of 1 with respect to y, so that will just be y. On the right-hand side, we can bring a outside the integral since it is a constant. Since we have the integral of a function being subtracted from another function, we can technically split that integral into two integrals so that we have the integral of 1 with respect to t minus the integral of e to the power of negative bt with respect to t. We know that the integral of 1 with respect to t is just t. As for the integral of e to the power of negative bt with respect to t, we can use u substitution. We can start by setting u equal to negative bt. We then differentiate both sides, and then we solve for dt. Now we substitute dt for du over negative b. We can take out 1 over negative b since it is a constant. We can then just integrate e to the power of u with respect to u, which is just going to be e to the power of u. We can then substitute back negative bt for u. And since we have solved the integral, we can now add our constant that we must solve for now. But before we can solve for c, we need an initial condition. Now, although it doesn't explicitly state an initial condition in the problem, we can infer one. We know that when t is equal to 0 seconds, the object hasn't moved at all. Therefore, its displacement is 0. So we have y of 0 equals 0. We can plug 0 into the expression that we have so far and solve for c. E to the power of negative bt, e to the power of negative b times 0 is just going to be 1, since anything to the power of 0 is 1. And remember to set the whole expression equal to 0 so that we can solve for c. When we do so, we get that c equals negative a over b. If we plug back the constant back into our final answer, this is what we get for our final answer. For the next part of b, we're asked to derive another expression, this time for the magnitude of the net force exerted on the object as a function of time. In order to answer this question, we need both mass and acceleration. And since we already have the mass, we just need acceleration. In order to find acceleration from what we are given, we need to differentiate the equation for velocity of the object. On the left-hand side, we know that the derivative of velocity is just acceleration. As for the right-hand side, we can pull a outside the derivative since it is just a constant. Since we have the derivative of a function being subtracted by another function, we can rearrange the derivative such that we have the derivative of the first function being subtracted from the derivative of the second function. For the derivative of 1, we get 0, and for the derivative of e to the power of negative bt, we can apply chain rule where e to the power of negative bt is the outside function and negative bt is the inside function. Therefore, we multiply the derivative of both functions. The derivative of e to the power of negative bt is just e to the power of negative bt, and the derivative of negative bt is just negative b. When we multiply the two, we get negative b times e to the power of negative bt. When we simplify this, we get a times b times e to the negative bt. Now that we have our acceleration, we can plug in to get our net force equation. For the first part of C, we are asked for the constant of speed. Never mind. For the first part of C, we are asked for the constant speed of the object. Now we know that when the object is falling in the liquid, there must come a time when it reaches a terminal velocity. The terminal velocity is the constant velocity that we are looking for. Now we don't know what time it will reach said terminal velocity. However, we know that when it does, the object will maintain that velocity for as long as it is in the fluid. Based on this, if we observe when time approaches infinity, we can get our answer by observing how velocity changed, since at that point when time is near infinity, the object will have already reached terminal velocity and maintained it. So to show that mathematically I've set a limit for the velocity function as time approaches infinity, we must solve this limit in order to find our terminal / constant velocity. We can pull a outside the limit since it is just a constant. Since we have the limit of a function being subtracted by another function, We can rearrange the limit such that we have the limit of the first function being subtracted from the limit of the second function. The limit of 1 as t approaches infinity is just 1. As for the limit as t approaches infinity of e to the power of negative bt, we can simply plug in infinity for t and evaluate from there. Using the exponent rules, we can rewrite e to the power of negative b times infinity as 1 over e to the power of b times infinity. E to the power of b times negative infinity, e to the power of b times infinity is an infinitely large number. Since we have 1 over an infinitely large number, that basically equates to 0. So we have a times 1 minus 0. You can then evaluate the remaining expression as a. Therefore, our constant velocity, which is our terminal velocity, is equal to a. For the second part of C, we are asked to find the force exerted by the fluid on the object when constant velocity is reached. Since this problem asks to solve for a force, it is important to draw a free body diagram first. As you can see, the two forces acting on the object are the drag force exerted by the fluid and the gravity force exerted by the earth. Since we are solving for the force exerted by the fluid, this means we are solving for the drag force. We first start by writing out Newton's second law. We then write out the forces acting on the object, which are the drag force and gravity force. Then we set the expression equal to 0. The reason we can do this is because the object is currently at constant velocity. The only two times when there is no net force on the object is either when the object is at rest or at constant velocity. Since the object is at constant velocity, it has no net force, therefore its net force is equal to 0. In order to solve for drag force, we can add the gravity force to both sides. This will give us the expression that the drag force is equal to the gravity force. Therefore, in order to find the drag force, we must evaluate the gravity force. To do this, we will rewrite gravity force as mg. Now we know what both the mass and gravity constant, we have both the mass and gravity constant. However, the reason why only the gravity constant is plugged in is because we need to convert the mass to the correct units before we can plug it in. Now that we have the correct units for mass, we can plug it in to evaluate the drag force. After evaluating, we get our final answer as 0.12 newtons.